Welcome to a journey into the heart of data-driven decision-making. In a world saturated with information, the ability to discern patterns, understand uncertainty, and make informed choices is no longer a luxury, but a necessity. Today, we're going to unlock the language of evidence, delving into the essential statistics that empower us to navigate this data landscape with confidence. Whether you're a business leader, a researcher, or simply someone curious about the world, mastering these fundamental statistical concepts will provide you with an indispensable toolkit for extracting meaningful insights and making choices backed by solid reasoning. This isn't just about crunching numbers. It's about developing a profound understanding of how evidence speaks to us and how we can listen effectively. At its core, statistics is far more than just compiling charts and calculating averages. It's a scientific discipline that provides a framework for understanding and making decisions in the face of uncertainty. Think of it as the grammar and vocabulary for interpreting the vast amount of data generated every second. We use statistics to collect, analyze, interpret, present, and organize data. But the real power lies in its ability to allow us to make inferences about a larger population based on observations from a smaller sample. This is crucial because, in most real-world scenarios, examining every single data point is either impossible, impractical, or prohibitively expensive. Statistics equips us with the tools to quantify risk, identify trends, and draw robust conclusions, transforming raw data into actionable knowledge. The bedrock of all statistical reasoning is probability. Simply put, probability is the measure of the likelihood that an event will occur. It's expressed as a number between 0 and 1, where 0 indicates an impossibility and 1 indicates absolute certainty. When we flip a fair coin, the probability of getting heads is 0.5, because there are two equally likely outcomes. Understanding basic probability allows us to quantify the chances of different outcomes and forms the basis for more complex statistical analyses. We often encounter two types: theoretical probability, based on reasoning, and empirical probability, based on observed frequencies from experiments. For instance, knowing the probability of a product defect helps a manufacturing company make decisions about quality control, or understanding the probability of a specific customer behavior can inform marketing strategies. Building on basic probability, conditional probability introduces the idea that the likelihood of an event can change if we have additional information. It asks, what is the probability of event A happening, given that event B has already occurred? This is incredibly powerful. For example, the probability of a customer buying a specific product might be low generally, but the probability of them buying it could be significantly higher. This leads us directly to Bayes' theorem, a fundamental principle that describes how to update the probability of a hypothesis as more evidence or information becomes available. Bayes' theorem is a cornerstone of modern machine learning, medical diagnostics, and countless other fields where continuously refining our understanding based on new data is essential. It enables a dynamic, evolving approach to evidence, rather than a static one. To move from individual events to broader patterns, we introduce the concepts of random variables and distributions. A random variable is a variable whose possible values are numerical outcomes of a random phenomenon. For instance, if you're measuring the height of students in a class, each student's height is a value of a random variable. A probability distribution, then, describes all the possible values a random variable can take and how often it takes those values. It's like a map that shows us the landscape of possible outcomes. For discrete random variables, which can only take specific, distinct values, we use probability mass functions. For continuous random variables, which can take any value within a given range, we use probability density functions. Understanding these distributions is key to grasping the underlying structure of our data. While there are many types of probability distributions, a few are particularly common and incredibly useful for data-driven decisions. The normal distribution, often called the bell curve, is ubiquitous. Many natural phenomena, like human height, blood pressure, or measurement errors, tend to follow a normal distribution. Its symmetry and predictable properties make it foundational for many statistical tests. Then there's the binomial distribution, which models the number of successes in a fixed number of independent trials, each with only 2 possible outcomes. This is useful for things like customer conversion rates or defect rates. The Poisson distribution, on the other hand, describes the number of times an event occurs in a fixed interval of time or space, such as the number of calls received by a call center in an hour or the number of accidents on a highway stretch. Each of these distributions provides a lens through which we can understand and predict different types of real-world phenomena. Since examining every single data point is often impractical, we rely on sampling. Sampling involves selecting a subset of individuals from a larger population. The goal is for this sample to be representative of the entire population, allowing us to make inferences about the population based on the sample data. Once we have a sample, we use estimation to approximate unknown population parameters. Point estimates give us a single best guess for a parameter, like the sample mean as an estimate for the population mean. Interval estimates, such as confidence intervals, provide a range of values within which the true population parameter is likely to lie, along with the degree of confidence. For example, stating that we are 95% confident that the true average height of all adults is between 165 centimeters and 175 centimeters. Understanding sampling and estimation is vital because it quantifies the uncertainty inherent in drawing conclusions about a large group from a smaller one. Perhaps one of the most remarkable and foundational theorems in statistics is the central limit theorem. This theorem states that, regardless of the original distribution of a population, the distribution of the sample means of that population will tend to be normally distributed, as long as the sample size is sufficiently large. This is incredibly powerful. It means that even if the underlying data is wildly skewed, if we take enough samples and average them, those averages will form a bell curve. This theorem is the reason why many statistical tests, which often assume normality, can be applied to a wide range of real-world data, even when the individual data points aren't normally distributed. It provides a robust justification for using normal distribution properties to construct confidence intervals and perform hypothesis tests on means, making it a cornerstone of inferential statistics. With a solid grasp of probability, distributions, and sampling, we can now tackle one of the most crucial tools for data-driven decisions: hypothesis testing. Hypothesis testing is a formal procedure used to evaluate the validity of a claim or hypothesis about a population parameter, based on sample data. It typically involves setting up 2 competing statements: the null hypothesis, which represents the status quo or no effect, and the alternative hypothesis, which is what we are trying to prove or detect. For example, a null hypothesis might state that a new drug has no effect on blood pressure, while the alternative hypothesis claims it does reduce blood pressure. We then collect data, perform statistical analysis, and use the results to either reject the null hypothesis in favor of the alternative or fail to reject the null hypothesis. It's a rigorous, evidence-based approach to making decisions. In the process of hypothesis testing, 2 critical concepts arise: Type 1 and Type 2 errors, and the p-value. A Type 1 error occurs when we incorrectly reject a true null hypothesis, essentially, a false positive. We might conclude a drug works when it actually doesn't. This error is often denoted by alpha. A Type 2 error occurs when we fail to reject a false null hypothesis, a false negative. This means we fail to detect an effect that actually exists. This error is denoted by beta. Balancing these 2 types of errors is crucial. The p-value is the probability of observing data as extreme as, or more extreme than, what we've actually observed, assuming the null hypothesis is true. A small p-value suggests that our observed data is unlikely if the null hypothesis were true, leading us to reject the null hypothesis. It's important to remember that a p-value does not tell us the probability that the null hypothesis is true or false. It only quantifies the strength of evidence against the null hypothesis. The applications of these statistical concepts are virtually endless, spanning every industry and discipline. In medicine, hypothesis testing helps determine the efficacy of new treatments. In finance, probability distributions model asset prices and risk. In marketing, A/B testing, a form of hypothesis testing, compares different campaign strategies to see which performs better. However, it's equally important to be aware of common misinterpretations. P-hacking, where researchers manipulate data or analyses to achieve statistically significant p-values, can lead to misleading conclusions. Confusing correlation with causation is another frequent pitfall. Just because two variables move together doesn't mean one causes the other. Moreover, ignoring the context of the data, the quality of the sampling, or the practical significance of results can render statistical analyses meaningless. A statistically significant result isn't always practically important. These are critical considerations for anyone using data to make decisions. We've covered a significant amount of ground today, from the fundamental concept of probability to the powerful framework of hypothesis testing, all while understanding the crucial role of distributions and sampling. The language of evidence, spoken through statistics, is not about finding absolute truths, but about quantifying uncertainty, understanding likelihoods, and making the most informed decisions possible with the data at hand. It provides a structured, objective way to interpret the world around us. By understanding these essential statistical concepts, you gain the ability to critically evaluate claims, design robust experiments, and transform raw data into a narrative of insights that drives progress. Embrace this language, and you'll find yourself empowered to make smarter, more confident choices in every aspect of your life and work. Thank you for joining me on this exploration of essential statistics.